So this is the surface area of the Gaussian. Oh, sorry. So this is the surface area of the spherical cell. So all these charges is enclosed within this Gaussian surface. Okay, that part is simple. Now, what about the left-hand side? So if you look at the electric field, so electric field will be pointing in radially outward direction. This will be always, if I look at this Gaussian surface, so electric field will be always pointing radially outward. So in that case, my E vector will be the magnitude given by the unit vector r cap, so which represents your unit vector, which is radially outward. And what will be the ds vector? The ds vector is again will have a magnitude of any, if I take any surface on the cell. So this is ds, that is the area of the surface, and the direction will be again radially outward as well. Okay, so ds will have a magnitude, whatever the surface, the small surface area that we are talking about, and given by r cap. Okay. This vector E, another characteristic, E, the magnitude of E. So if I look at any point on this surface, okay, if I look at any point on the spherical surface, the magnitude of E will be always a constant. Okay, so if I go to another point, the value of E will be different. But as long as I am on any of these points on this sphere, so the magnitude of E will be same. This is another characteristic of the electric field. So that I can write now E dot ds will be equal to, both have the same direction, so it will be simply E into ds. Okay, so that will be my dot product. So the left hand side we have simplified, and what we also found out that this electric field is also constant when r fixed. So the smaller r, so then E will be constant. So then let's use this and see how the left hand side will look like. The left hand side now will become E surface integral, because E is now constant, so I will take it out from the integral. So I have to integrate over the surface, small surface area. And if I do integration over the whole surface, so which is spherical in nature, so this will be E into the area of the surface, which is 4 pi small r square. So we are talking about, so this ds represents the Gaussian surface. So the Gaussian surface has a radius small r, so therefore the surface area will be 4 pi r square. The left hand side is now simplified. Right hand side also we have simplified. So we have E into 4 pi small r square will be equal to Q enclosed by epsilon naught by sigma into 4 pi r square divided by epsilon. So my electric field, the magnitude of the electric field will be equal to sigma 4 pi r square divided by epsilon naught. So which will be sigma into r square. So 4 pi out, so I will have epsilon naught r square. So the electric field will be, I can write it something like sigma, so 1 over r square into r cap. This is the vector. This is the vector down radially outward direction. Okay, so this is the electric. The, the one thing what you clearly notice that this electric field, the magnitude varies as a function of r square. All these things are constant basically. So now, what about inside the cell? What will be the electric field? So I'll take something like this. Okay. Somewhere, this is my point P prime, and I want to find what is the electric field inside. Surface again as a sphere because of the symmetry of the problem. So that is why the Gaussian surface we are taking as a sphere or a shell, spherical shell. So this is what we have. Apply the Gauss's law over the surface will be equal to Q enclosed by 7. Now, charge enclosed by this Gaussian surface. So let's say call this S prime. So instead of S. So what is the charge enclosed by this surface S prime? It is 0 because all the here on the shell. So therefore, the Q enclosed is equal to 0. So that means your electric field will be 0 inside the cell. So when R is less than the capital R, so E is 0. So we can write down E is equal to 0 when R is less than R, and it is sigma R square by epsilon R square R cap when R is greater than. Okay. So this is what the electric field is. So we have to find out. So that we have not found out yet. So only what using the Gauss's law, we know what is the electric field outside and inside. So now what is the potential? The potential is normally how we define. We define as a line integral. So if I want to find the potential at any position R due to a particular charge distribution or due to electric field, so with respect to a reference, and normally the reference, so you take from whatever the reference point to that point, and you calculate this line integral of E dot dl. So, and most of the cases, this reference you choose at infinity. Okay, so this is one of the convenient thing that we use in electromagnetism, so that most of the times the potential will be 0 at. Okay, so this is what we will use, and again we will look at it different the cell, and one is inside the cell. So let's say again look at the case 1. So R is greater than R. So we know E, the electric field, is given by sigma R square by epsilon R square R cap. And what is dl? So dl vector is a length element. Again, it will be pointing in a radially outward direction, dr into R cap. So this is again the situation something like this. So you want to calculate what is the potential at point P. Okay. So what we are saying, you go to like almost infinity and you integrate over this line integral. That line joins from infinity to this point P. That therefore the length element will be equal to the radially, again because of the symmetry. So we are saying dl, the length element will be. So if you substitute all this in your equation, so it will be minus infinity to small r to the given by epsilon r square. So E dot dl, so again they both are in the same direction, so it will be given by. So sometimes not to confuse too much, so what you can do is you can take this variable. something else like dr prime, and this is r prime or dash, so whatever you want to call it. So you can give a name. So this variable is not r but r prime. So now let's perform the integration. So again, so you have a lot of constants which we can take out. dr prime by r prime square. So which will be equal to, so r prime square, if I take a integration of that, so it will be minus from infinity to r. So now if I calculate, so minus 1 by infinity. So this is 0. So what I have is minus, so there is two minus signs, so it will be plus sigma r square by epsilon naught r. So the potential is again, you have sigma r square by epsilon 1 over r, where is as 1 over r, and this is. So this is again very similar to what you have seen for one single charge. So if I take one charge, charge particle, isolated charge particle, the potential also varies for that, for isolated charge particle. This charge particle having charge Q, so the VR varies as Q by 4 pi epsilon naught r. Very similar expression. Okay. So the potential inside. So again, we will use the same. But what we will do now, we will again two parts. Remember, electric field is 0 inside. Okay. So this electric field is 0. But the potential may not be 0. So we'll see what will be the value. So from, so I take this, so we have a point which is inside the cell R. So I integrate the electric field from infinity. So this is, let's say, infinity from here to any point going radially out. So this will be minus infinity to R E dot dl. So then we will simplify it. So what I will do is I will divide into two regions. So I will change the limit of the integration. So I'll first integrate from E, from infinity to capital R. So some on the spherical cell, and then minus R to small r E dot dl. So this is, and this is inside. Okay. So this inside will be 0 because electric field is 0. So what we have is only the outside, which is given by this integral infinity r dot d. Okay. So we know what is E outside. So it will be exactly the same like what we calculated in this case. Only thing, now the limit of the integration is not from small r but up to capital R. So therefore, so the value of VR will be equal to sigma r square by epsilon naught. So there is, in place of 1 over small r, I will have 1 over small capital R. So this will be equal to sigma r by epsilon naught constant. Okay. So the electric field, the potential inside the spherical cell is constant. So if you plot this VR as a function of R. So you'll get this is constant, and then there is a 1 over R dependence. So up to R equal to the radius of the cell, so it is constant, and then as 1 over R. So this is 1 over R. Okay, so exactly the same way you can do it for a spherical of a if a sphere has a charge distribution, a volume charge distribution rho. So you can use the same trick that we have used, but only thing what will happen now, so within inside the sphere, the electric field will not be anymore zero. Okay. So if I take a solid sphere, so here we have taken a shell, but if I take a solid sphere, so that means I will have some charge distribution. So in that case, normally you say this is the charge distribution, the volume charge distribution rho. Therefore, if I take anything inside the sphere, so the charge enclosed by this Gaussian surface will not be zero. So accordingly, you have to modify your electric field and potential as well. Okay. So then we'll see another application, which is again given in your problem. So this is the question number 8. This is the question number 8 of your terminal questions, I think, from application of Gauss's law. So the problem is so we take a coaxial cable, okay, so which I will draw now. So we have a coaxial. So this is again a cylinder that we are talking about. So this is quite long, and this is made up of copper. So this is a copper wire, so to say, okay, which has a linear charge density lambda. Both are made up of copper. Sorry. So both are made up of copper. So the inner one, the inner cable, has a charge density minus lambda. Then the outer one has a charge. So the outer cable has a charge density plus. Okay, so now the question is, what is the electric field in, so I will define 3 regions. I will call as a region 1. Okay, so this is my region 2, and this is my region 3. So what is the electric field in 3 regions? So what is the electric field inside the inner cable? What is the electric field between the cable 1 and cable 2, that is the region 2? And what is the electric field of this coaxial cable? So this is the problem. So this has a cylindrical symmetry. So we have to use a cylindrical, like a Gaussian, apply the Gauss's law. But in it, the Gaussian surface will not be any more like in the will be a cylinder. Okay, so this is what we will use now. Okay, so if I draw, so let's say one. So we are one first. So I will look at this inner cable right now. And Gaussian surface. Again, I draw a Gaussian is a cylinder. Okay. So the Gaussian surface that you draw is arbitrary. It is up to your choice. So because of the cylindrical symmetry, we are drawing a Gaussian surface as a cylinder, which has a radius small, exactly the length of the cable. Okay, so this is the length. So we'll take exactly the length of the cable as the Gaussian surface. So again, let's look at the Gauss's law. So we dot ds will be equal to q enclosed by epsilon naught. So what is the how much charge is in this Gaussian surface? So it is all the charges that is residing or on the cable. So which has a linear charge density minus lambda. So all the charges that is on this, so I did it, so not in the region 1, but so for the region 1, because we are interested only in the inner one. So let me redraw this. So this will be for region 2, not for region 1. So let me erase it. So for region 1, so I have, this is my copper, okay, and I want to find anywhere in between. But we know this is a conductor. This is made up of copper, so this is a conductor. And remember, for conductor, the side is always 0. Okay. So why it is the case? Because all the charges always will come to the surface, because any conductor has lots of free charges, the free electrons, and that is why they conduct electricity. So when you apply electric field, so a lot of free charges are available which can move. So now when you are applying electric, charges will move, and what they will do is, if I take a conductor, and so all these free charges, for example, so if I apply electric field like this, electric field happen, the negative charges come to, for example, to the surface, and automatically it will create a positive surface on the other side, and then you have an electric field which is, so let me make it big. So what you have is, so you have electric field which is opposite to this external electric field. So this external electric field is applied in this direction, and it is opposite to this. So the induced electric field within the conductor, so due to this charge separation, so it will be the opposite to this electric field. That's why electric field within the conductor, so this E, will be always 0 for any. Okay. It makes the life simpler in region 1. So when we talk about region 1, then because it is a conductor, so the electric field inside will be 0. So now what about region 2? Like what I was discussing. So for region 2, which is in between the first cable, the inner cable and the outer cable. So in that case, we will surface. Okay, so which has a length radius r. Okay, so this is not the same as the outer cable. So it is a different a Gaussian surface. What is it? Is an imaginary surface that we are drawing, and we have to apply the Gauss's law. The Gauss's law tells us dot ds over the surface will be equal to q enclosed by epsilon naught. Now, what is the total charge uh, that is within this cylinder? So how much charge is there? So all these charges that is sitting on this inner cable, so they are all within this Gaussian cell. And what is that value? So this Q enclosed plus lambda into L. Okay, so this is your minus lambda. Okay, so this is minus lambda into L. Total charge that is enclosed by the S. Easy to find out the right hand side. What about the left hand side? Now again, we will be looking at certain characteristic of this electric field. The ds vector, for example, will be in a surface area, so it has a magnitude, and the unit vector will be radially outward, r cap. Okay, so this is again the cylinder. If you look at a cylinder and the surface area area vector of a cylinder, so it will be radially outward. Okay, so in this, so this is my cylinder. So it is radially outward. Okay, so this is the surface area. Now, electric field similarly has the same characteristic. It is again radially outward, and it will be a constant on this Gaussian surface. Okay, so the same characteristic that we used for the spherical cell. So we can then write down this integral E into ds. So this is my left hand side. So which again I can take the electric field out because it is constant, and the area of the total area of the Gaussian surface is the area of my cylinder, Gaussian cylinder, so which is given by 2 pi r into L. So now I can find out what is the magnitude of the electric field, so which will be given by minus lambda L by epsilon naught, or my electric field magnitude will be given by minus lambda by 2 pi epsilon naught 1 over r. So again, there is a 1 over r dependence, that is the magnitude. And what is the direction? So it is minus lambda by 2 pi epsilon naught 1 over r. It is along the radius of this cylinder, r cap, which is radially inward. So the minus sign. There is a minus sign. Okay, so this is for region 2. What about region 3? So region 3 means we have the inner cable, the coaxial thing, so minus lambda. Then you have the outer cable, which has a plus lambda. So our Gaussian surface would be completely outside, so region 3. Okay, so again, you can draw a Gaussian surface in region 3. Okay, which tells us now you have to find out what is the total charge enclosed within this Gaussian surface. So what will be the total charge? So it can be easily found out because you have one is a minus lambda, the other one is plus lambda. So when you add up, because of the both, so it will be one is minus lambda L, the other one is plus lambda L, so it will be 0. So that means in region 3 also the electric field is also 0. Okay, so quite simple. So in only you have an electric field in the region 2. So region 3, the electric field is 0. Region 1, also electric field 0. Only the electric field exists in the region 2. So this was again similar thing which we discussed for a parallel plate capacitor yesterday as well. So where we talked about this situation where you have both carrying a charge density sigma. So the electric field here is not 0, here it is 0, and here it is also 0. Okay, so sometimes what happens in the problem they ask, so in the problem they asked that sigma, this is not same, so this is sigma 1 and sigma 2. So in that case, so E is not equal to 0 in any of these regions. So you have to be careful what is asked. So whether the charge density is the same or different. Okay, so this kind of problem sometimes will come. Okay, so next we will discuss another interesting technique that is normally used to calculate this electric field and potential. Okay, so another thing which also you should be careful about when so in exam it might come that it will be given like a function, for example, or any function, any vector function E, or let's say I'm writing a vector function F. So a function would be given. Okay, so then what would be asked is like find out whether represents an electric field. For example, I write F is yeah. Okay, so this is some vector function, and it is asked tell us whether this will actually represent an electric. So all vector function will not be electric field. So in this case, what you have to do, you have to find out two conditions or two things you have to find out. So one is del. You see, look at what you are getting, the curl of it. So for an electrostatic field, so this curl of a F should be 0. If that is the case, and this one should be like so like we saw del dot E should be equal to rho by epsilon naught. So this constant. So it should depend on the charge or something like that. But the curl of the vector has to be 0. So in that case, this is not the sufficient, this is a necessary condition for the electric, for a function to be called as an electric. So if you find the curl of this vector, for example, in this case, not 0. In that case, it is not, it can never represent an electric field. Okay. So this is what sometimes also is asked. So you have to simply find out these two, del dot F and curl of F. And if curl of F is 0, so you could say this is a possible function which. Okay, so another thing which also sometimes is asked, like a scalar potential would be given or any scalar function. So you have to calculate what the gradient of that. So that is always an electric field. So if a potential is given or any function is given, which represents a scalar field, which is scalar function, if you take the gradient of that scalar, so you will get the electric. Now, if I take divergence of both sides, so what I will get? Okay, so I'm taking a divergence of both sides, so which will be what which we write as del square V. Okay, So this is a new operator, del square operator. Okay, so this is again an operator. This is a vector operator, still a vector operator, which is using a dot product in this case. Okay, so this is also used quite a lot in physics. And this formulation is used quite often also to find out the potential in case of a charge distribution. Because as you can see, like when we are writing this situation, so that means if I can find out the potential, there is a high chance I'll be able to find the electric field for a charge distribution. And since potential is a scalar function, it is relatively easy compared to electric field. So it is for a given complicated geometry, complicated charge distribution, it is usually easy to find the potential, and then from that you can find the electric field by taking the gradient. Okay. Now we know that del dot E is equal to rho by epsilon naught. So by that relation, so our del square V will be equal to minus rho by epsilon. So this is what how the del square V that is equal to minus rho by. So this is known as a Poisson's equation. Okay. So this kind of mathematical expression is quite common in other field of physics as well. So in dynamics, but also in quantum mechanics, in for example, fluid dynamics. This kind of expression are often encountered. So where you have to operate this del square on a scalar function to find out. So it's called as a Poisson equation. So that means, so this del square, so how will you calculate? So in a, so this is a partial derivative. Okay. So careful. So you have to write it in Cartesian coordinate, Cartesian, spherical, polar, and cylindrical. So this is part of your mathematical physics, able to write coordinate forms, coordinate systems. So if I take, for example, a one-dimensional situation, so in 1D, so this expression becomes d square v by dx square minus rho by epsilon. So there is also another form of this equation, this Poisson's equation. So where del square v will be equal to 0. So this is called as a Laplace equation. This is also one of the very famous formulation in, so which is used quite often to find out the potential. So now by doing an integration of this, so you'll see some examples. So by integrating this, so you'll be able to find out what is the potential. Now here del square v equal to 0 is what we are interested in certain region. But that doesn't mean that, so what it means, in that region, you don't have any source or any charges. So there is no charge density or anything in that region in which we are interested in finding out. So for example, so if I take a region like this, my charge distribution may be here. It has its own electric field, so it will have a potential. But if I want to know what is, like apply this equation here, so del square v in this region will be del square v will be 0 because there is no charge distribution within this region. Okay, but that doesn't mean there is no charge distribution. So there is a charge distribution here. It's far away from this region, but we are interested in this, which does not have any sources of that. Okay, so the trick here is we have to solve or we have to integrate, but we need some more conditions. Okay, so it is not easy to find a solution for this. We need something called as a boundary condition. To solve this differential equation. So this is again a differential equation. So we need something called as a boundary condition to solve this. What it means, 1D, the Laplace equation becomes d square v by dx square is equal to 0. Okay, so in one dimension. So del square v dimension in derivative d square v by dx square equal to 0. So if you find a solution, do the integration. So you will see something like ax plus b. So this is what you will find. So a okay. So vx is equal to ax plus b, where a and b are constant. So now these two are unknowns. Constant, but we don't know what is the value of a and b. So in order to find the v, we need a boundary condition. So the boundary condition will, if you apply this boundary condition, so we'll be able to say a and b will be known. Okay, so how many boundary conditions we ideally need? So in this case, we need two boundary conditions because we have two unknowns, a and b. So at least we need two equations. That means two unknowns are definitely required so that we can say what. So we will use this in a very interesting scenario or interesting case, which we call as a spherical capacitor. So there are several examples of how you can apply this technique to calculate the potential due to a charge distribution using this Poisson's equation and Laplace's equation. So I'm taking one example, a nice example here. But you can also do this same thing in case of for a parallel plate capacitor or a cylindrical capacitor. Okay, so again, you have to use the appropriate Laplace's operator in that coordinate system. Okay, so if I take a cylinder, so I have to use the cylindrical coordinates and I have to write the Laplacian operator in that coordinate system. Okay, so let me first draw this capacitor like a schematic of that. So I have, so I'll first define or say what is the problem and then we'll try to solve it. So I have a spherical capacitor, so two spheres. Okay, so capacitor means always you have two metallic plates. Okay, so this is a metallic ball surrounded by another metallic ball separated by some insulator or maybe some air, for example. There should be some gap between them. So the outer one is connected to ground, which has a charge minus q. It has a radius b. Then the inner one has a charge plus q, has a radius a. So that is what a typical parallel plate can. So you have two plates, one has plus q, the other one is minus q, and they are separated by certain distance. Okay. So here we have to use the spherical coordinates. Okay. So if I say for the total capacitor, the total, so plus q minus q on both the plates, the total charge for the system is of course 0. So which represents a situation your square v is equal to 0. Okay, but what is the del square operator here? So there is no theta or phi dependence. So you have only r dependence. So in that case, it becomes 1 by r del r square del v by del r to be equal to 0. So these kind of things you need to remember. If you write these expressions and practice it a little bit, then you will remember how the operator would look like in Cartesian. So in Cartesian, by del square by del x square. Okay, so that is simple. Only thing, the problems will be when you are writing in a spherical polar or a cylindrical polar. Okay, so you write down and practice a little bit, then you will remember. So, and most of the cases, you don't have to, or I would say, the cases you don't have to think of the theta or phi dependence. So typically, the r or the rho dependence would be good enough. Okay, so what I didn't say, what is the problem we need to find out. So we need to find out what is the potential V, electric field, and capacitance. So we need to find out all these things for this capacitor. Okay, so we have, this is our starting point. So as I said, we can solve it, but also we need certain boundary conditions. So what are the boundary conditions? So sometimes in some problems, you will see the boundary condition will be given to you. In this case, it may not be given, but you will be able to figure out what is the boundary conditions. Okay, so how to find out or figure out the boundary condition here? So again, if boundary condition is given, then things are easy. Okay, but if it is not given, still in this case, for example, we can figure out. So we know that the outer plate is grounded. So that means if R is equal to B, so what will be the potential there? It will be equal to 0 because it is connected to the ground. That is one boundary condition. Now, what will be the corresponding potential on the inner plate? R equal to A. So this will be a constant potential V0. So this is how you get a potential difference V0, 0 on one plate, and that is how you get, so one is at a lower potential, has a charge minus Q, the other one has a higher potential, has a charge, total charge plus Q. And there is a potential difference or electric field in between the plates. So this you can even figure out from the problem as well. So therefore, whenever you are solving, so just think a little bit, wait for some time. A lot of information you'll get from the problem statement itself. So read it carefully and then try to solve. So don't get panicked. Sometimes what happens, students get panicked looking at a problem. Sphere is given, cylinder is given, charge density is given. But if you just make a schematic, many of the times you will simplify the problem actually. Okay, so in electrostatic and magnetostatics, especially if you draw this kind of schematics, it is always helpful. Okay, so let's now integrate this function. Okay, so integrate means, so this r square term will, so what we have is, so we have, now I can write it as an ordinary differential equation. So I have only r dependence here, r square dv by dr is equal to 0. So that means this term has to be a constant. Okay, so then only if I take a derivative of this term, okay, so I am writing this term is equal to 0. That means this should be a constant. The constant of a derivative is a 0. So that means I can write down r square dv by dr is a constant a. Let's so I will write now dv is equal to a by r square dr. So now further integrate it. So my v of r, So this is integration of A by R square dr, which is given by my A over minus 1 by R plus B is again a constant. So now we know the R dependence for the potential. So this is 1 over R dependence. But this A and B are unknown. This is what we need to find out. And we can find out because we have boundary condition and we have two boundary conditions. So two equations. So we should be able to find what is A and B. So we have two unknowns and we have two equations. So we'll be able to find out the unknowns. So let's first apply the boundary condition 1. So we say VB when R is equal to B, this is 0. This is because connected to ground. So VB is equal to 0, which implies what will be V at R equal to V, or let's say V R equal to B, kitna hoga? So we'll just substitute. This will be A divided by B, small b plus capital B. So which is equal to 0. This is the graph. So that means I have at least, I know a relation between B and A. So B should be always equal to A, capital A divided by small b. Okay. Now apply the second boundary condition. So which tells us V A is equal to constant V naught. So again, so what will be the value of V when R is equal to A? So this is equal to minus A by A plus B, so which is equal to a constant V naught. And I know B is always equal to A by B. So this is my equation, let's say 1. This is equation 2. So I can write down that AA plus A by B is equal to V naught. So now if I simplify this is simple algebra. So which you will get, then A is equal to V naught AB divided by A minus B. So we have A, we have found what is A, we know what is B. So we can then simply substitute and we'll be write down this expression B, A minus B, 1 over R plus V naught AB, A minus B, 1 over. Okay, so which we will simplify further. So these are all simple substitutions which you can do at home. So this is the potential due to this capacitor. So what will be the electric field? So we'll take a gradient of this. Okay. So again, this gradient you have to take in spherical polar coordinate, which will be del by del R, VR into R cap. So now if you take the derivative, so the first term is a constant, that will be 0. So only 1 over R dependence will be there. And the expression will be equal to, so by simplifying, so I'll just write down the final expression. So 1 over R square into R. Okay. So potential we found, electric field we found. But how to find out the capacitance? So to find out capacitance, so capacitance we know C is equal to Q by the potential difference, which is V naught. So for one plate it is V naught, the other plate it is 0. So so the potential difference is V naught. So C will be equal to Q by V naught. So the main thing is how to find out what is Q. So again, we will take a little bit help from the Gauss's law here. So how? So we know from Gauss's law that E dot dA. So I'm not writing the integral yet. E dot dA will be equal to whatever the charge is enclosed by this surface, small surface area dA. Okay. So if I take the surface charge, so I have the plates on which I have the surface charges, sigma, the charge Q, for example, so which is distributed on the or some charges are distributed on the surface, having a surface charge density sigma, multiplied by this dA. So this sigma dA basically represents my Q enclosed kind of. Okay, so this is what this sigma dA represents. So this is what we are using the Gauss's law. So the electric field and the dA will be in the same direction. So I can write now the left hand side as EdA, which is equal to sigma by epsilon naught dA. Okay. Or sorry, so this dA, or let me write down first, different way. So so we don't know what is the direction of the area vector, but it has a magnitude dA and direction n cap. N cap is the normal to the surface. So then E dot dA will be E dot dA, magnitude, into n cap will be equal to sigma dA by epsilon naught, which tells us that E cap dot n cap, so dA and dA will cancel out, is equal to sigma by epsilon. So sigma, that is the charge density, is given by E dot n cap into epsilon. So just a moment. So this is the charge density, which we can use to find out the total charge Q. So if I have because it is a sphere, so the total charge Q will be equal to sigma into 4 pi, whatever the radius square. Okay. Now, the expression for electric field we know, and this n cap, again, as I said earlier, so the n cap, this is the unit vector for the area vector, will be radially outward because of the spherical symmetry. So it will be equal to r cap. So this E and n cap will be in the same direction. So we can then find out what is sigma first, the charge density, which will be given by epsilon naught. So we substitute the expression for E. E we have found here. If you substitute that, so you will get B naught AB divided by B minus A 1 over A square. Okay. This is what we want to find out the charge density on, for example, the plus Q charge on the inner plate or the inner sphere. So it will be sigma into sigma into 4 pi A square. That is the radius of this inner sphere. So now you substitute all these terms and simplify. What you will get is 4 pi epsilon naught B naught AB divided by B minus A. So we know what is Q, and the V naught we know, so the capacitance will be equal to Q by V naught, which is equal to 4 pi epsilon naught AB B minus A. Okay. So you can use the same way to find the capacitance of a cylinder. So when where the plates are like the one is inner cylinder, the other one is outer cylinder, or as a parallel. So this is one technique which is quite often used, and I think you will find at least one question from this kind of this part in your exam as well. Okay, then there is another very interesting technique. So before going into that, so if you want to take, so I'll give you 2 minutes break, and then we will start. So this is 7:10. So we'll start at 7:12. Okay, so 2 minutes break you can have, and then join again. Okay, so let's start again. Uh, so there is another very interesting technique we have to find out the charge distribution, sorry, the potential due to a particular kind of charge distribution. It is only applicable in certain situations or in certain cases. Okay, so it is not applicable for all cases or all situations, but it is for particularly few cases. It is very useful. So this is known as a method of images. This is a very powerful technique. Okay, so there are several techniques that have been developed for this electromagnetic statics and magnetic problems. So method of images is also very interesting technique. Okay, so let me first pose you the problem and then we'll see how the used in that case. So let me take a infinite sheet of conductor. Okay, so this is a ground conductor, infinite, let us see, extended over infinity, and we have a charge q. So let's say it is. So if I take the coordinate something like this, and I say this is at a height d with respect to this. So what will be the potential due to such a? Now remember, we have a charge q here. So you cannot say this is not an isolated charge. We also have another conductor. And we want to find out what is the potential at any point above this conductor. Okay, so not so this technique that we are going to talk about is not applicable for anything when you want to find out below this infinite conductor. So anything above the conductor, what do because of this charge. So this is not an isolated charge anymore. So why? Because I have a charge plus q here, and if I put a conductor here, so what I will have is, if it is a positive charge, so I'll have the induced charges on the surface, so which have a charge density minus sigma. So that means the total charge of the configuration different, not a, the potential will be different. Okay, so in this is a if you want to solve using Gauss's law or any other, for example, using this Poisson's equation, it is very difficult. So here, what is used something it is called as a uniqueness theorem. So you may go through this theorem in your course material, so it will be very easy to understand. So what we want to do is, or what this uniqueness theorem, that if you want to find out, so for or let me put it in a way, so it doesn't matter how the charge distribution is or what configuration you have. Now if you find a situation, okay, so where the potential that you have found or the potential that you have written down satisfies a certain boundary condition, okay, and this boundary condition is unique to that for that potential, so then however you have found this potential doesn't matter. So this potential will be a true or the correct potential. So there will be no other potential due to whatever distribution that you have looked at. So irrespective of looking at the charge distribution or the configuration, what you need to do is, let's say in the problem, you first find out what are the boundary conditions. Now try to guess or find a potential which satisfies boundary condition. You can find such a potential. That potential will be unique and it will be actually the potential due to that configuration. So you say, so let's say in this case, this problem. So what are the boundary conditions? Let's look at. The boundary condition. So let's say we define, this is our x, y, z axis. So on this, I define something like that. So let's say this we call as a z plane where the conductor is. Okay, so this is this represents is z equal to 0, the conductor. So we know because conductor is grounded, so one boundary condition is clear. Z at z equal to 0, v should be equal to 0. Another boundary condition is that if the point P, this point P, the point P is far away from any of this configuration, that we know. If I say this point P is far from the configuration, okay, so in that case the situation will be x squared plus y squared plus z squared is much greater than d square. So in that case your v is also will be equal to 0. So this is the boundary condition 1, and this is a boundary condition 2. Now this is what, so any potential which we obtain from this configuration should satisfy this boundary condition. Okay, so now we will look at another version of the, not this problem but another problem. So what I will do is, I have a certain axis and I have a charge q here, which is, I'm saying 0,0d, okay, and I put another charge minus q exactly at the same distance. This is a mirror, something like you have put a mirror here and you have taken an image of this charge q, so which has a minus q at 0, 0, minus q. Now find out what is the potential at a point P here on this side. So this potential at any point P will be equal to q by 4 pi epsilon of r divided by what is the distance. So this is, let's say, r1, this is r2, so it will be q by 4 pi epsilon 1 by 1 over r1, 1 over minus r. And what will be r1? R1 will be x square plus y square plus z minus d whole square, or r1 square, or r2 square magnitude is x square plus y square plus z plus d whole square. So if you substitute, so you'll find what is the potential. Now let's look at what is the boundary condition for this situation. So at z equal to 0, what is the total potential at P due to this configuration? So it will be both will come out to be x square plus y square plus d square. So r1 and r2 will be exactly the same. So this will be 0. And also, if I take the point far away from this configuration, so where x square plus y square plus z square is much greater than d square, so there Vp is also equal to 0. So now look at this boundary condition and look at this boundary condition. They are exactly the same. Okay, so V will be 0 when Z is 0, and V will be 0 when the point is far away from the charge distance. So that means the potential that we have obtained here will be the same potential that would have been obtained if I solve this problem as well. Okay, so this is what we call as a method of images. So if I have a problem where you are given that you have a conducting sheet, infinite sheet, and there is another isolated charge, and you are asked to find out the potential due to that charge distribution. So what you do is immediately you use wherever the plane is, so you replace it by a mirror, and then try to find out what is the mirror image of that charge. Also, you have to change the sign of that charge. So if it is plus q, it will be minus q. And so this is a mirror reflection, and find out what is the potential due to this charge configuration, isolated charge. Then it is simple, and you will be able to find the potential very easily. So I'll give you another example. So I have, let's say, two perpendicular such sheets. Okay, so infinite conductor. So all both are grounded. Okay, and I have a charge plus q here. And you are asked to find out what is the potential due to this configuration. So what you do is, again, you use the method of images. So this infinite sheet you replace by two perpendicular mirrors. So this is one mirror, this is another mirror. I have the charge q here. So let's say this is as a coordinate a and b. This is a, this is b. So now I have to find out the mirror images. So I'll go on this direction. So this will be minus q, having a coordinate minus a and b. I'll take another mirror image. So this is minus q. This is a minus b. And then again, since I have created these charges, so they will also have a mirror image. So I'll take another one which has a plus q, having a coordinate minus a minus b. So what now? So this problem is exactly equivalent. So there is no difference between these two problems actually. So if you find out what is the potential at this point P due to this charge distribution, so all these four minus q plus q minus q plus q, you'll be able to write down what is the potential at point P. So this is very easy. Why? Because you will write this as q by 4 pi epsilon naught. Then you see what is R1, what is R2, what is R3, what is R4. So this is 1 over, for plus, it will be 1 over R1. If it is a minus, it will be 1 over R2. This is 1 over minus R3 plus 1 over R4. And then you will be finding this R1, R2, R3, R4 in terms of A and B, X, Y, Z, and A and B. So this will be easy to find out because you know your coordinate geometry. So you know how to find out R1. This has a coordinate, so Q, A, and B. So you know what is the coordinate here. You know what is the coordinate. This is A, B, and 0. This is X, Y, Z. So you'll be able to find what is R1, what is R2, R3, R4, and the potential. So similarly, there is another problem I'm telling you. So you can easily use this method of images. So again, I take a conducting sheet like this. I have one charge plus q here, which are 0, 0, d. I have another charge 2q here at 0, 0, 2d. Okay, so this distance is g. This is also d. Now this is again a grounded conductor. So only thing is this need to be a grounded conductor. Okay, a conductor and grounded. So then again, so the equivalent problem is, so you put a mirror. So this is plus q, this is plus 2q. So you take a mirror image minus q, minus 2q. So this is 0, 0, g, d. This is 0, 0, 2d. This will be 0, 0, minus d, and 0, 0, minus d. So now find out what is the potential at this point due to this 4 charge distribution. Again, so this you simply write, which will be equal to for this charge, for this one Q. So again, R1, R2, R3, and R4. And you know what is the coordinates? 0, 0. This is quite clear, x, y, z here. So you find what is 1 over 4 pi epsilon. 1 will be only thing you have to be careful. One is plus q, the other one is plus 2q charge. So one is minus q, this is minus 2q charge. So for R2 and R4, the charge is twice. So that is the only thing you have to take care of. And simple, you will find the potential. So this is the method of images, which is very powerful, but applicable in only certain cases. So this is also applicable in sometimes, so in the book you will find it is also given for spherical thing, but most of the time the questions are confined to this planar symmetry. Okay, so the other type of question that I have seen is related to dielectrics or related to polarization. So I'll describe that. So we have two types of materials. One is we call as a dielectric, the other is a conductor. Okay. So what is a conductor? Conductor has at least one or many free charges. So there will be unlimited free charges from a conductor. And where these charges come from? Free charges come from? So it comes from the atoms or the electrons which are loosely bound to the atom. So if I take, for example, a copper or aluminium, so typically what you have is at least one or two electrons will be not really part of any or really bound to any atom. Okay, so those electrons are called as free electrons. Now those electrons can move very freely if they see an electric field. So this is what the characteristic of a conductor is. But in a dielectric, you don't have those such free charges. You might be having, but mostly the electrons are kind of bound to the atom. So the electrons are strongly bound to these atoms, and therefore their response to an electric field is very different. So as I said, if I put a conductor in an electric field, so the electric field inside the conductor is zero, because you have all these induced charges which will come to the surface, and electric field, it will oppose the electric field and it will be zero. So for example, if I take a sphere, this is a conductor, so and I apply electric field like this, so what will happen? So I'll have the electrons will come to this surface. So automatically this surface will become positive. So I have an electric field which is in this direction, which opposes this electric field outside, and therefore the total electric field inside will be zero. But this situation will be different of a dielectric. So this E total is not always zero, or not, definitely it is not zero. So why it happens? So for that, we will look at a simplistic model, and we will look at a single atom and see how an atom will respond where there is no free electron, okay, no free charges. So atom, you have a nucleus, and then you have electron. So it is like a charge cloud, so to say, which has a spherical charge distribution, let's say. So it is, you have a very symmetric or a spherical charge distribution or a charge cloud of electron which surrounds your nucleus. Okay. So now it has a radius, for example, A. So what will happen if I apply an electric field in this direction? So this is what we are talking about, is an atom. Okay. So we have drawn it in a bigger picture, but actually the sizes are small. A, for example, if I take a hydrogen atom, the radius is Bohr radius, which is of the order of 1 angstrom, or less than a 0.5 angstrom. Okay, 0.53 angstrom. So now if I apply electric field to that atom, so what would happen? I will have, so this nucleus, the positive charge will move in the direction of the electric field. So what we'll have, let's say, so there will be a certain displacement of this positive charge. And if I have an electron cloud whose charge center is at the origin initially, the spherical charge distribution, it is exactly the charge center will be on the positive charge. So that charge center, so the electron cloud will be a kind of a bit shifted now. So this electron cloud will shift and the charge center will be somewhere here of the negative charge. So what you have is a separation of a positive charge and a negative charge separated by a distance d. And that creates a dipole with a dipole moment q into d. So this is a dipole moment, electric dipole moment due to this electric field. So what you have done is you have created a dipole in the atom because of this electric field. Okay, so this is called as an induced dipole. Okay, now if I take let's say uniformly, so let's say again, let's look at the electrostatic problem from that point of view. So is it like if I apply the electric field, so if I have this charge separation, so is it going to like just move away from each other? Is it like the D will keep on increasing? It is not. So there will be a situation where an equilibrium will be established where when the positive charge, for example, let's say going away from the negative charge, so this negative charge will try to push it or pull it towards it or attract it. So there is an external electric field which is trying to take them separate away from each other. But once the separation happens, so there is an electric field due to the negative charges which will try to pull the positive charge towards it. So there will be an equilibrium. So how much electric field is produced due to this spherical charge distribution? So if I have an electron cloud, which is we represent as a spherical charge, so what will be the electric field due to that? That electric field is given by, you can use the Gauss's law actually to calculate this electric field at a distance d. So we want to find out what is the electric field. So now, so the situation is like I have a charge distribution. Okay, so this is my charge distribution rho, or let's say I have a charge q on a sphere. Okay, and I want to find out what is the electric field. This is the center. What is the electric field due to this? This is a negative charge. So what is the electric field due to the spherical charge distribution at a point D here? So this is, you can use the Gauss's law actually. So try to do that. It is again quite simple. Like we have used it for spherical cell, you can do it for this charge distribution as well. So in that case, what you will find, this electric field will be given by 1 by 4 pi epsilon naught q d by aq. So this is the radius of the sphere. Okay, so that means at equilibrium, this electric field that is produced due to the electron cloud or the spherical charge will be equal to this external electric field, and then so a dipole has formed, induced dipole, and it will be stable. Okay, so which will be equal to our 4 pi qd by aq. Now this qd term, if you look at this qd term, we said this is the dipole moment, p. So p is equal to the dipole moment. So that means our E and P they are related. How they are related? So I will write this P is equal to 4 pi epsilon naught AQ into E. So that means my P is directly proportional to the electric field. Okay, so this relation, which is given by this term alpha, so P is equal to alpha E. Okay, so due to the electric field, so you induce a dipole having a polarizability. So alpha we call as the atomic polarizability. Okay, so this is what an electric field does to an atom when so when an electric field is applied to an atom, this is what happens. An induced dipole is formed. So you can find out this polarizability, atomic polarizability. So sometimes in the question it will be given, for example, a particular atom. So H atom, hydrogen atom, or helium, or so if what you need to know is what is the value of A. So this will be given. So what is alpha? Alpha. So we know this relation. So alpha will be equal to 4 pi epsilon naught AQ. So epsilon naught is the permittivity of free space. So which is a standard constant, so which you will substitute. And if you substitute all these values, so you will be getting this number. The one thing you have to be careful about the units when you are doing these calculations. So everything should be in SI unit, preferably. So then there will be no mistake. Okay, so now let's say if the further question is asked, so let's say I have applied an electric field, so which is of the order of this. So this is the magnitude of the electric field that I have applied. So what is the distance between the dipoles? So what is the value of T? Okay, so how do we find out? So to know, so we know P is equal to alpha E, or that implies Q into D is equal to alpha into E. So that means E is equal to alpha E by Q. So what is Q here? So this is you are taking a 1 electron. So Q is equal to 1.6 into 10 to the minus 19 coulomb. So alpha we have calculated, E is known. So this is again, you have to make sure that it is in the SI unit. So you substitute that. So D will come out to be 6.9 into 10 to the power minus 15 meter. Okay, so I think in the exam calculators are allowed, so you can use those and find out this values. So you see how small it is, but still there is some separation. Okay, so due to the electric field, you have this induced type. So then there is also sometimes a question could be asked. So there are two types of dielectric. So one is a polar, another is a non-polar. This again, if you go through the text, you can find out what are the differences. For example, so for polar will be you have a permanent dipole moment. So for example, if I take water, so I have a permanent dipole moment. So how? Because of the structure itself. So this is how the water molecule looks like. So you have positive, positive, and negative. So the positive center will be here, and you have a dipole moment. So this is B. You have a dipole moment. Okay. So this is a permanent dipole. Non-polar is like any other atom where you apply electric field and you induce a dipole. So this is an induce dipole. Okay, so you can then write down other differences between polar and non-polar dielectrics, and you explain like what is how why this is polar, why this is non-polar. So sometimes also it will be asked like what will be the torque on the dipole moment due to electric field. So those things you can look, very simple expressions are there, you can understand it easily. So another interesting thing which should be aware of here, so which we call this P, which is called a polarization. So this polarization is a vector which is defined by a dipole moment per unit volume. So this is another important a vector which is, so that means when you apply an electric field, so your dielectric become polarized. So you have a polarization. And what will be the value of polarization? So this is equal to N into P. What is N? N will be equal to number of dipole moments per unit volume. So each dipole has a dipole moment P. There are N dipole moment per unit volume. So my polarization is equal to N into P. We know that P is proportional to E. So my polarization is also proportional to E as well. So which is normally is written as chi epsilon naught E. The chi is known as the susceptibility. Okay. So this thing is quite simple to understand if you go through the text. So what I will tell you quickly is, so there are many things associated with that, but I will just tell you a couple of things which are important. So one thing is, what is the field due to this polarization P? So what is the electric field due to this polarization P? So there will be definitely a change in the electric field in dielectrics. So due to this polarization, okay. So one is you get an electric field due to the other isolated charge distribution and so on. But by applying an electric field, now since you have induced a polarization or you have made a new form of this alignment of charges, so that also can affect the electric field as well. Okay, so this is very easy to extrapolate. So if I take a dipole, for example, and I want to find out, so this is my dipole, and I want to find out what is the dipole moment, the potential due to this dipole at point P. So this is given by, sorry. So this is given by this expression for a dipole. So R cap dot P dipole moment divided by R square. Okay, so this is the potential due to dipole at a distance R. And what is this P? P is nothing but, so if I take the relation between the small p dipole moment and polarization, it is small p into d tau. So d tau will be, this is the volume d tau where the dipole is situated. So because dipole moment is, polarization is dipole moment per unit volume. So if I multiply by the volume, so I'll get the dipole. So then if I substitute that, so I will get, and if I integrate over the whole volume here, so this is my volume. So I will get so I have many such dipoles here, okay? So which give rise to the polarization P. So when I add up all these dipole moment per unit volume, so I will get the polarization. So that means if I want to find out the potential, so So I have to integrate over the total volume, which is over d tau prime. Okay. So this term, so one can use some trick is there, which where you use this operator 1 over r, which is equal to r cap by r squared. Okay, so this is again you can prove as well. This will be part of your mathematical physics, I guess. So if you do that, so you can write this expression in a very interesting way. So you will be using this term and integration by parts. If you do that, so sometimes they ask this kind of derivation in the exam. So if you do that, so what you will write, so eventually you will find out your VR, you'll be able to write as 1 by 4 pi epsilon naught the surface R dot dA prime. So you will separate your integral into two parts. One is a surface integral and one is a volume integral. 1 over R del dot B theta. And which is simplified or written sometimes. So this is similar to what we have seen earlier, some expressions as well. So this is something like a sigma dA, sigma dot dA by R minus 1 by 4 pi epsilon naught 1 over R charge density over volume. Okay, so this is the potential due to a volume charge density, and this is due to a surface charge density, the potential. And what is the volume charge here? The volume charge here, what we call as del dot P, and the surface charge, we call it as E. This is due to the dipole moment, which is given by basically this is P dot dA. Okay. So any polarized material, so what you can do is, so when you want to find out a potential due to any polarized material, so you can say like there is certain surface charge on the dielectric material and there will be certain charges within the volume, and both will contribute to the total electric field or to the potential. And this is how so the volume charge will come out as a divergence of the polarization, and the surface charge will come out as a divergence of your dipole moment. So these are all what we call in dielectric as a bound charges. So the B symbol that we are writing is for bound charges. Okay, so these are not imaginary charges, but they really exist within your dielectric. So this they form because you are inducing the polarization, or you have a permanent dipole, so the molecule itself has a dipole moment. So these are the reasons why you have this dipole moments. Okay, so you could find out this bound charges if you know what is the polarization or what is the dipole moment. If I take, so one example I will give you so that you will be able to find out at least what is the field inside a dielectric. So I take, let's say, a material. So in simplistic case, so I take a dielectric which has a positive charge, a separation of positive and negative charges. Okay, so this is at electric field 0. But when I apply the electric field, so what happens? So you separate the positive charges and the negative charges. So the positive charges, let's say, will be here. This is represents the sphere for positive charges, and you will have negative charges as well. Now, whatever is the cross section, they will all cancel out. So now what you have is a situation, is a a positive separation of a positive charge and negative charge. Okay. So which are separated by a distance d, let's say. And these are all surface charges. So these are all surface charges on the sphere. So what is the electric field inside due to the surface charge? So again, you can use the Gauss's law, so which is given by rho d by 3 epsilon naught. So this you can also use the Gauss's law. So this is again, if I have a surface charge distribution having charge density rho, what will be the electric field inside? Okay, so like what we did for an atomic case, so it's the same formula we are using. So this is inside, so which is given by rho d divided by 3 epsilon. And what is rho? Rho is your charge by volume. This is the density. So E inside will be equal to minus Q d by V divided by 3 epsilon naught. So Q into D is your dipole moment, and this will be simply equal to minus P by 3 epsilon. So the inside electric field will be given by the minus of polarization by 3 epsilon. So just by using a simple separation of these charges with a distance d, so you could find out what is the electric field inside the dielectric. So there are other methods as well, but this is one of the simplest way. You can also find out the electric field outside as well, but for that, in that case, you have to first use for one single dipole and then add up all the things. So, but this is not really necessary in this case. So this is another example where it is very useful is a capacitor. So this is again a very simple idea. You can use it for a dielectric. So I have here both conductor, another conductor. This will be minus charge. So they will induce these charges like that. Okay. So I'm drawing this because you should also do this in the exam. It will be asked to draw these things. Okay. So you'll be drawing this kind of situation if a capacitor is with a dielectric is given. So what will happen? So then, so this is your dielectric when it is a part of a capacitor. So this is the distance d between the plates. So you have the charges Q, which is given by C into V, and so you will find out what is the capacitance. So without any dielectric, it will be epsilon naught A by D, but this capacitance will change to this permittivity of the dielectric when you introduce this dielectric. So another thing which also could be asked about this relation, del dot E is equal to rho. So how this changes for a dielectric? Okay. So if I look at a dielectric, so I have now two types of charges in a dielectric. So one is this rho. There will be free charges plus there will be the bound charges. These bound charges are due to the induced dipole or due to the dipole moment that is present. So that means my expression will be del dot E will be equal to rho F plus rho V. So sorry, this is epsilon naught. This will be like that. Now I know this rho V will be equal to del minus del dot P. So this is what we saw earlier, minus del dot P. So my del dot E into epsilon naught will be equal to rho F minus del dot P. If I take everything to this divergence to the left hand side, so I have a term del dot epsilon naught E plus P is equal to rho F, so which is to define a new vector del dot D is equal to rho F. So this D vector, which is we write as epsilon naught E plus P, is called as an electric displacement vector. Okay, so which is a different than the electric field that is present inside or applied. So due to the polarization, this electric field has changed to this electric displacement vector. And your Gauss's law is now changed to this form. Okay. So this T, which is epsilon naught E plus P, and P is chi epsilon naught E. This is what we saw earlier. So this is proportional to E. So D will be equal to 1 plus chi. So if you substitute that, it will be equal to E, which is sometimes written as epsilon E. So this 1 plus chi, which is given by epsilon R. So this is the dielectric constant of the material. Okay. So the permittivity, epsilon is the permittivity of the material, epsilon R is the relative permittivity of it. So this is called as a linear dielectric material. Linear, why? Because there is a linear relation between P and E, D and E, and so on. So this relation, so therefore changes, the Gauss's law changes in a dielectric medium. Okay, so I'll stop here. What I suggest that you look at some of the problems that is already discussed. So I'll not be able to discuss everything here in the class. So another important thing you should look at from dielectrics is a Clausius-Mosetti relation. This might come as in your exam as well. I expect that. So you should look at that also. Okay, so if any question. So if not, so I'll stop now and we will meet tomorrow at 4 o'clock and discuss some more problems and some more techniques from magnetostatics, which will be useful for your exam. Okay. So thank you.
Okay, sir. Thank you, sir.
Thank you.
Yes, sir.